Hi everyone, I'm Brendan, and I'm going to present about a paper called Monte Carlo Geometry Processing, a grid-free approach to PDE-based methods on volumetric domains by Sawhney and Crane. So suppose we wanted to solve a PDE like the Laplace or Poisson equation on a geometric structure. Sawhney and Crane's idea is to avoid meshing challenging geometric structures with finite element methods, which can be time-consuming for detailed objects such as the fly on the left. Instead, they use Monte Carlo integration to find an approximate solution. The Monte Carlo approximation is noisy at first, but can be refined by taking more samples, shown on the right. In my implementation, I focused on solving the Laplace equation. To solve the Laplace equation, Sawhney and Crane use a technique called walk-on spheres. The idea stems from the fact that the solution of a harmonic function at point P is the expected value of the first point on the boundary reached by a random walk starting at P. By symmetry, we can find this boundary point by sampling uniformly on spheres. As shown here, we start at x0 and successfully sample boundary points x1, x2 until we get to point xk, which is close enough to the boundary where we know the value of the function. So now I'll show you my demo. So the boundary condition here flips whenever the sum of the x and y position increases by 2, and the boundary segments are this rotated U here, shape here, and the cross in the middle. I've initialized the Laplace equation solution with 8 random walks on spheres. And by pressing a button, I can reduce the variance of the Monte Carlo solution by taking more samples. The end result is much less noisy than initially. Thank you for listening.